Welcome to the Explainer. Today, we're jumping right into constructions and tilings. We're going to look at how the strict logical rules of geometry actually connect directly to the creative ways we solve everyday spatial puzzles. You know, whether you're an aspiring artist trying to balance a drawing or just someone trying to tile a kitchen floor without making a total mess, this explainer is going to show you the hidden mathematical toolkit at play. So let's dive right in.
Let's kick things off with a totally relatable challenge for artists. Honestly, it's a challenge for anyone who's ever doodled a face in a notebook. How do you draw perfectly balanced, symmetrical eyes? Usually, you sketch one beautiful eye, and then you painstakingly try to guess the proportions for the second one, right? And, well, usually it ends up looking a bit lopsided. But what if you didn't have to guess? What if there was a flawless, logical way to map the whole thing out? Look at the incredible symmetry in these artistic examples. Achieving this level of perfection isn't just about having a remarkably steady hand or years of practice. It actually relies on hidden geometry, mapping out the lower and upper arcs of the eyes. Behind the artwork, there's literally an invisible framework dictating exactly where every single curve should fall. Now it gets really interesting when we strip away the art and look strictly at the abstract geometry. See those overlapping arcs? They're anchored by a hidden supporting line, basically an invisible horizontal axis running straight through the middle. And even more crucially, there are unseen center points. Let's call them A and B. These act as the true anchors for the entire drawing. Literally everything stems logically from those two little dots. So what's the actual mathematical secret to this visual symmetry? Well, it's all about ensuring equal distances. If we label the outer corners of the eye X and Y, then for the eye to be perfectly symmetrical, the distance from our center point A to both X and Y must be exactly the same. And the exact same rule goes for center point B. The formula for this is super simple. AX equals AY, which equals BX, which equals BY. In plain English, the radius of the upper and lower arcs must be completely identical.
Section 1. The perpendicular bisector. Finding the centers. So, to find those unseen center points from a totally blank slate, you use the simplest tools imaginable, an unmarked ruler and a compass. First, you place the sharp point of your compass on point X and draw identical arcs floating above and below your line. Then you do the exact same thing from point Y. Just make sure you absolutely do not change the compass width. Second, you carefully mark exactly where those arcs intersect each other. Bam! Those are your magic points, A and B. Finally, you just connect A and B with a straight line.
Now, by definition, bisection is simply the division of a line, or any object really, into two absolutely identical parts. But a perpendicular bisector, that goes a vital step further. It perfectly cuts that original horizontal line in half at a flawless, exact 90-degree angle. It establishes true, mathematically perfect balance. But hold on, how do we know this process actually works without breaking out a protractor to measure it? Well, mathematics demands proof. By comparing the triangles formed by these intersecting lines, we prove something called congruence. Side AX equals AY because, remember, we use the exact same compass radius for both. The exact same logic applies for BX and BY. And of course, they share that middle side, AB. Because all three sides match perfectly, the triangles are identical twins. This undeniable logic guarantees that flawless 90-degree intersection right in the middle. This beautifully illustrates the final proven result. You can see the midpoint labeled O, dead center. Because those larger triangles we just talked about are completely congruent, the two angles right at point O absolutely must be identical. And since they sit on a flat, straight 180-degree line, each one has to be exactly 90 degrees. We haven't just drawn a neat little line, we've mathematically proven that it's perfectly perpendicular.
Section 2. Expanding the toolkit. Angles and parallels. Let's see how this builds our ability to map out more complex spaces. You know, once you master the perpendicular bisector, you've essentially unlocked the next level of geometry. You can use that exact same unmarked ruler and compass to construct highly specific angles entirely from scratch. You want to drop a perfect 90-degree angle anywhere on a line? You can do it. You can cut existing angles perfectly in half to copy them. You can even construct a flawless 60-degree angle just by creating intersecting arcs that form an equilateral triangle. It's incredibly empowering to create such absolute precision with such simple tools.
You can even create perfectly parallel lines. Lines that will never ever intersect, no matter how far you draw them, using these exact same principles. No measuring tape required. By carefully setting an angle on one line and then transferring that exact arc length and angle up to a new point with your compass, you can draw a second line that is mathematically guaranteed to be perfectly parallel to the first.
Section 3. The logic of tiling. covering entire surfaces.
Okay, so we've talked a lot about drawing lines and dividing open space, but what happens when we want to completely cover entire surfaces? Tiling is defined as covering a region using a set of shapes without leaving any gaps or having any pieces overlap. And tiling isn't just some weekend home improvement chore for your bathroom floor. In mathematics, it's actually a profound and deeply satisfying puzzle about calculating area, respecting boundaries, and utilizing pure logic.
A brilliantly classic example of this kind of spatial reasoning is the ancient Chinese tangram puzzle. It uses exactly 7 specific geometric shapes, 5 triangles of varying sizes, 1 square, and 1 parallelogram. The challenge here is to use these exact pieces to perfectly tile different silhouetted figures without a single tiny overlap. It forces you to mentally rotate and construct shapes within very strict geometric boundaries. And that brings us to a fantastic logical challenge from the source material. Imagine you have a rectangular grid that's 5 squares wide and 7 squares long. Can you cover it perfectly with rectangular domino-like tiles that are 2 squares long by 1 square wide? Take a second. Really try to visualize how you might lay those out in your head.
Let's look at the math before you try to mentally force those pieces onto the board. If we had a 4x7 grid, we'd have an even number of rows, right? So we could just lay all the tiles vertically, side by side. Super easy. But a 5x7 grid has an odd number of rows and columns. 5 times 7 means there are exactly 35 total squares to cover. Now here's the undeniable logic. Since every single tile covers exactly 2 squares, any grid you successfully cover will always contain an even number of total squares. 35 is an odd number. Therefore, without even touching a single tile, we logically know it's mathematically impossible.
Section 4. The Geometric Toolkit. Core Principles Summary. It's time to step back and briefly recap the core principles we've unlocked today. We learned that simple bisection creates the foundation for perfect symmetry when drawing complex shapes, like those artistic eyes. We found that perpendicular bisectors allow us to pinpoint exact midpoints at flawless 90-degree angles. We saw how a compass and a straight edge give us the power to build precise angles and perfectly parallel lines without ever needing numbers on a ruler. And finally, we discovered that tiling requires strict logical deduction of area, like our odd and even square rule. From art to architecture, geometry literally gives us the logical toolkit to solve spatial puzzles. Which leads me to leave you with this final, hopefully provocative thought. Look around the room you're sitting in right now. Seriously, take a look. How many hidden perpendicular bisectors, exactly duplicated angles, and perfectly calculated tiles are silently holding your physical world together? Mathematics isn't just trapped in textbooks. It's the invisible, beautiful blueprint of absolutely everything around you. Thank you for joining me for this explainer, and hey, keep looking for the geometry hidden in plain sight.